In this video, we are going to explore the four subsets, or sometimes called the subspaces, of matrices. And what we're going to be doing is we're going to bring together the idea of the null space, the row space, and the column space, and now something new called the left null space. So let's define what the left null space is. Suppose A is an n by n matrix, then the left null space of A is written as L, the cursive L of A, is the null space of A transposed, and this will be a subset of the complex complex vectors of size m. Now note that the left null space of A and the column space of A are subspaces of the complex numbers with m entry, and the null space of A, not the left null space, but the null space of A and the row space are the subspace of the complex vectors of n entries. Let's just look at an example here where we're asked to find the column space, the null space, the row space, and the left null space. So here's a nice small little vector where we take our matrice. Here's our nice little small matrice that we do the row reduced echelon form, and because R is 1 and N is 2, the column space of A is just the first column, 1 and 3. The null space of A is we take this, set it equal to 0, and we write the free variable, or the dependent variable, which is x of 1 in terms of x of 2, the free independent variable. Now if we transpose this and we do the reduced row echelon form, we still have, in this case, not always, in this case we still have the R being 1 and the N equals 2. That means my row space is just my first column, which is 1, 2. And then the left null space is I find the null space, writing my dependent variable in terms of my independent variable, which is, of course, x sub 2 and x sub 1. So when we are looking at the column spaces, where we are at this point is we can use the definition. It's the given columns, the column space of my matrix are just whatever columns are given to me. We can also find a linearly independent set of columns like we did when we were in the LDS sections, which was linearly dependent spanning sets. We can transpose the matrix and put it into RREF form, kick out the 0 rows, and then write the remaining rows as column vectors. We can augment on, this is the new one, this is new. So we're going to augment the matrix that is an n by n matrix with an identity size m. We're going to row reduce it. We're going to build a matrix from the rows that have zeros in the first n columns, using only the last m columns of the augmented matrix, and find the null space of that smaller, like submatrix almost. Let's go through an example. Now, suppose I start out with this being my matrice. The normal way of finding the column space is just say, here's my columns. Here's my first column, my second column, my third column, and my fourth column. The next way that we learned was to find the column space that was linearly independent. So we took our matrice, RREF'd it, and we got this. And because the pivots are in columns 1, 2, and 3, then we use columns 1, 2, and 3. So again, that's something we've learned, nothing new there. The next way that we can do that is we can transpose it. So we transpose our matrice, starting with my matrice up there, and I transpose it, RREF it, and I get this. Then my column space is this row as a column vector, this row as a column vector, and then again this row as a column vector. We know from previously that T is linearly independent, and it's a subset of the column space being everything. Just like W here is linearly independent, and it's also a subspace of the column space of my original vector. And then the last way, which is new, what we do is we take our matrice, we augment onto it the identity matrix of size m, and we get this. Now what we do is we pay attention to this part right here. We're not worrying about this part. We use this information to give us this like a submatrix sequence, and we call it L. And then the null space of that would be, I would be taking this and finding the null space, which would give me the 2, 0, 1, 1 half, 0, 0, 1, and 0, 1, 0. And this is also the subspace of the column space of A, and it is also linearly independent. So now we have found a fourth way of doing it. And the reason we do this is because we are going to use these properties. We're going to define what it means to be in the extended reduced row echelon form. And once we do that, we get information from that gives us our 4 subspaces. So we look at our matrix. We augment on the identity matrix of its size M. We row reduce it into this new matrix N. And then we take out the pieces that we want. So we end up with, when it's in the row reduced form, the B matrix being the new identity and the J matrix being the inversion of A, if it's invertible. If it's not, then it's just this information. And then we get these 4 matrices. We have the 0 matrix down here. We have this C matrix, we have this K matrix, and we have this L matrix. So let's go back to this matrix that we had, and we augmented on it, and we got to here. Now notice I introduced these 2 lines. These 2 lines breaks this up into the C matrix, the K matrix, the L matrix, and then I have my 0 matrix right there. That leads us to the next theorem that says, supposes A is an n by n matrix and n is its extended row echelon form. Then J is non-singular. B is equal to J times A. If X is a vector in the complex numbers with n entries, and Y is a vector of the complex numbers of m entries, then if I take my matrix A, multiply it by my X vector, I will get the Y vector. If and only if my B matrix, and this is where the J and the B are coming from up here, then my B matrix multiplied by X must equal my J matrix multiplied by Y. Again, I'm getting the B and the J here, which if we look at our example, before we kind of partitioned off that matrix, this would be the B matrix, and then this side would have been the J matrix. So when I'm talking about the J is non-singular and B is equal to J times A, that's what I'm talking about, B being this, where we took this matrix and it turned into the reduced row echelon form, and the J matrix being the reduced, or the identity matrix gets turned into the J matrix, which is square. C is in reduced echelon form, so I'm going to go back to the way I described it before. So I'm going to come back up here. Let me just erase that. This part here is my C matrix, and C is in reduced row echelon form, has no 0 rows, and has R pivots. I have 1, 2, 3 pivots here, so I have 3 pivots. L is in reduced row echelon form. This is L down here, and has no 0 rows, and has M minus R pivots. Now M is 4, and R on my example up here was 3. That means I should have 1 pivot, and that's true. So the proof is in your book for your viewing pleasure. Go ahead and take a look through that. What we get, though, from this, so now we're ready to really talk about where we are and what we're trying to do, is suppose A is an n by n matrix with extended echelon form n. Suppose the reduced row echelon form of A has R non-zero rows. Then C is the submatrix of n formed by the first R rows and n columns, and L is the submatrix n formed by the last m columns and the last m minus 1 rows. Then, this is what we get. This is the important things. The null space of A is the null space of C. The null space of A is equal to null space of C. And you're thinking, well, wait a minute, what's going on here? Well, let's rewrite it down here again. If we take, I just want to take it and write this again. If we take our A matrix, augment on our identity matrix M, we end up with this matrix, which is C, K, 0, and L. So this is what I'm referring to in all of this theorem right here. So let's zoom back in and take a look at now what I'm saying. So the null space of A is equal to the null space of this submatrix C. The row space of A, my original matrix, is the row space of C, this smaller submatrix. The column space of A, my big matrix, is the null space of L. That's this little column, this little subvector or submatrix down here. The column space of A is the null space of L. The left null space of A, that's L, not script L. The left null space of A is the row space of L, L being this matrix. This means the script means the left null space. That script is left null space. The non-script is just telling me I'm the subspace of my matrix. We call it L. And I know it's a little confusing. Is equal to the row space of L. So what that means is that we can find all four subsets by just finding the null space and row spaces by taking my matrix A, augmenting on my identity matrix, and then what shakes out is all of the four subspaces. So let's go through an example here. So here's my matrix. I'm going to augment on my identity matrix, and then I'm going to reduce row echelon form. This, again, I have 1, 2, 3, 4, 5, 6 columns. So I go over 6 columns, 1, 2, 3, 4, 5, 6. So here's my augmentation. Then I take and kind of section off any of the rows on the left side of the first 6 columns, the left side, the side that we had initially. Any of the ones that have rows of 0, I section those off. And then what I'll end up with then is this is my C, this is my K, this is my 0 matrix, and this is my L. From that, I can find the null space of A. So the null space of A is equal to the null space of C. So here's my null space, or here's my C. This is my C. And the way I find my null space of C is just like I did before. So the null space of C is I find my first row, which is x sub 1 plus 0x sub 2 plus 2x sub 3 plus, and you're getting this, right? You're getting the idea that we do it just like we did before when we're doing the null space. So that's no big surprise. So in other words, what I do is that this would represent the coefficients. This would represent the coefficients on the free variable, which is x sub 3, because this is the column with my free variable. This would represent the coefficients on my x sub 4, because that's a free variable. And this would represent the coefficients on my x sub 6, because that's the free variable. So the null space is what we've already learned, nothing new there. And of course, it is just the opposite sign. So -2 in the first position, -1 in the first position, and -3 in the first position in the first row of the null space. And then of course I would represent x sub 2 all the way across, then x sub 3, x sub 4, x sub 5, and x sub 6. Or position 1, not x's, excuse me, position 1, position 2, position 3, etc. Okay, then the row space of A is equal to the column space of C. The row space of A is equal to the row space of C. So 1, 0, 2, 1, 0, 3 is this first column. The next column is 0, 1, 4, -6, 0, -4. And of course, then my third column. My column space of A is equal to the null space of L. And of course, L is a 1/4 matrix. That means this one is a free variable, this one is a free variable, and this one is a free variable. So this would be the coefficients on the free variable x sub 2, x sub 3, and x sub 4. So you can see that this first position would be a -2 for the x2, -3 or -2 for the x3, and -4 for the x4. And then of course I'd have a 1 in the second position, 0, 0, 0, 1, 0, 0, 0, 1. That's nothing new. And lastly, the left column space, or the left null space, is the row space of L. The left null space of A is the row space of L, which is just this vector. And that is pretty much it. There is some things to help you decide how to get to the column space or the row space. You can find the column space by the definition of a column space. You can find the column space by the basis of the column space. This is where we have the linear independence. We can find the column space by finding the null space of L. This is from, we just learned from the 4 subspaces. We can find the column space of A by using the column row space and transposing it. So that, again, up until now, the only thing that's new is this one right here. This one's the one that's new. All the rest we've already learned. Or, notice that we have these little arrows. I can find the columns, the row space of A is defined by the row space of the matrix transposed, which also is referring back to the column space. The row space is the 4 subspaces. Again, this is the new piece. The row space can be found the basis of the row space. We did that before. And then definition of the row space of a matrix. Now, a couple of things you should really pay attention to. That row operations do not preserve the column spaces. So when you're doing row operations, you are not necessarily preserving the column spaces. However, row operations do preserve row spaces. Just something to keep aware of when you are looking at the homework.